joining the webinar. Tony, Sam, thank you for putting this together. I know we have quite a few represented from Produce, so thank you, and a few others that were able to dial in. So again, as I mentioned earlier, with a big group like this, a little bit harder to have a two-way conversation, but again, it's very informal. If you have any questions, please stop me and ask. I do have a lot of information to get through in an hour, so I do go fairly fast. So please stop me if you have any questions, and happy to discuss anything you guys want to discuss. So with that, I'm going to go ahead and share my screen, and then Tony, if you can just confirm that you do see my, oops, start at the beginning. The beginning usually is the good place to start.
Yes, I can see your screen.
Obvious. Awesome. Should have a Dytran white page. And we'll get her started. All right. All right. Thanks again for joining us on this webinar. Again, this is Dytran Instruments. We are a manufacturer of piezoelectric sensors and accelerometers, predominantly for dynamic measurement. We do vibration, pressure, and force, but we also offer DC-based accelerometers for low frequency, low G applications as well. And today we're going to talk predominantly about piezoelectric dynamic vibration monitoring is what the subject matter is today. Just a couple comments about Dytran. Again, we're predominantly talking today about piezoelectric sensors. We're very fortunate at Dytran to support some of the premier aerospace and space customers in the world. Our largest customer over the last 10 years has been SpaceX. We put probably around 75 sensors on every launch that goes up. They have a big launch scheduled May 27th, the first time astronauts have been sent to the space station from American soil since the space shuttle was retired. So anyway, exciting times in the space industry, but we also do a lot of turbine engine work in aerospace and a lot of automotive applications as well. Dytran is located in Los Angeles, California. I cannot afford to live in California, so I have a home office in Ohio, so I get over and support Tony and customers in Indiana as often as possible. I do cover the automotive industry for Dytran as well, so I'm very familiar with our turbine and aerospace sensor lines, but very familiar with our automotive product as well. We are a family-run business. We started in 1980 in Buffalo, New York. For those that might be familiar with the accelerometer industry, it really started in two locations. One was in the universities of California back in the 1950s through Endevco, and then the other was through a gentleman named Walter Kistler in Buffalo, New York. All of the accelerometer companies since then came from those two organizations. The Dytran DNA comes from that Kistler PCB Buffalo, New York area. So our founder was president of Kistler and president of PCB before he started Dytran. We have about 190 people at Dytran, so a small family-run business. And we do have an extensive stocking program at Dytran. Quick delivery is very important. Those sensors do come with a lifetime warranty. And we also offer inside machining. We have 22 CNC machines at Dytran. So raw material come in and sensors get shipped. Just to give you some perspective, we shipped 35,000 sensors out of our factory last year. Okay. If you're ever in California, we would love to give you a tour. We're very proud to show you our processes and people. These are the topics we're going to go through today. Again, I can change gears as needed. If there's a certain topic you guys would like to discuss, calibrations or whatever it might be. I'm not going to go through the list. We're just going to jump right into the presentation. So today we're talking about piezoelectric sensors. Normally when I'm doing this presentation in person, I like to hand out sensors just so you see what these things look like, the shapes and sizes of these sensors. But In lieu of that, we'll just talk about it. So Dytran and our competitors have been making these sensors, as I mentioned, since the 1950s. So literally over 70 years of developing sensors for measuring vibration using piezoelectric technology. And yet, even today, we still make new products out of this technology. And the reason we still use it and we can still make brand new products with it is for these reasons. We can make literally the world's smallest accelerometers, 0.2 grams in mass, 6 millimeter cube triaxial sensors. And so most of our customers are looking for small, low mass sensors for their testing, whatever product they might be testing. These sensors also have a very simple 2-wire amplified system where the output and the common ground ride on the same wire. It's a very innovative amplifier that we use to amplify these sensors internally. We'll talk quite a bit about that amplifier here in this presentation today, but it allows us to provide a very simple 2-wire system right to your data acquisition system with a coaxial cable. We offer wide dynamic range, so we go from micro Gs, literally measuring seismic events or civil structure, industrial applications where they're looking at bridges and buildings moving, all the way up to pyrodynamic events. So we go from 0.2 Gs all the way up to 100,000 G with the same technology. Same thing, wide temperature range. We offer cryogenic sensors that are rated to -320 F all the way up to plus 1200 F for turbine engine monitoring. So almost a 2,000 degree swing from one piezoelectric sensor. We're also going to talk today quite a bit about MEMS DC accelerometers because we do offer those as well. So we'll compare and contrast quite a bit today between piezoelectric sensors and MEMS DC sensors. There's no way you could ever do -320 to plus 1200 with a MEMS accelerometer. So that's another unique feature of this piezoelectric technology. Very low noise. We do a lot of studies on MEMS sensors. Again, the sensor that's in your iPhone is a MEMS analog devices a DC accelerometer. It's a triaxial sensor. And the industry keeps getting better, lower noise with the MEMS sensors. However, if you took an O-scope and you plugged a piezoelectric sensor in and a MEMS DC sensor in and you shook them, you would still see exponentially difference in the noise level of a piezoelectric sensor. It's extremely low noise. Even though MEMS is getting better, piezoelectric is still exponentially better as far as noise. And then lastly, I will say broad frequency range. We offer sensors that go from 0.2 hertz all the way up to 20 kilohertz with this technology. On the MEMS side, they are getting better. We have a new product that now goes up to 7 kilohertz with a MEMS DC sensor, which is quite impressive for that technology. Common uses for piezoelectric sensors. Basically, anybody that manufactures any product typically has to test it for environmental stress screening. So whether it's an iPad, a mouse, or a muffler, or a helicopter, it has to be vibration and environmentally tested. So our customer base at Dytran is typically automotive, aerospace, consumer products, oil and gas, things like that. A lot of that stuff has to be vibration tested. I want to talk a little bit about just the documentation that comes with your sensor when you acquire it or when you're selecting the sensor. The first thing we want to talk about is that document on the top right called the 127 or the outline installation drawing. And it has very important information, the dimensions of the sensor. It has the mounting recommendation. It'll have the recommended mounting torque. If it's a thread mounted sensor, it'll have material. It'll have surface preparation, surface finish preparation, things like that. So anything related to mounting the accelerometer, very important document. And then off the website, you will get the specification sheet, the data sheet of the sensor. From top to bottom, I know it's impossible to read right here, but if you open a data sheet from any of our suppliers, Dytran or anyone else, it usually will go start with the mass and the size. We always start with mass and size because we're always concerned about mass loading your test. You just don't want to test the tip of a pen with a sensor the size of a coffee cup. So we constantly worry about mass loading. So the first thing you want to look at is the size and the mass of the accelerometer, then the sensitivity, the frequency, the G range, the temperature rating, whether it's isolated or not isolated, the electrical termination. Those would be the main things that we look at when we're looking at a data sheet. We also then provide plots. These would be typical plots of frequency, temperature response, and phase for each data sheet, or for each sensor on the data sheet. And then let's talk a little bit about the very, very important calibration certificate. So each sensor that is shipped comes with a certified 17025 ISO calibration certificate. Just a couple data points on this. You can't really see it, but we start our standard calibration for a piezoelectric sensor at 20 hertz, and then we go up to the maximum full-scale specification of that accelerometer. On this one, it happens to be 20 kilohertz. So we give you 10 points from 20 hertz to 10 kilohertz. We then plot those points down here to give you a typical frequency response plot. But I want to highlight that up here in this, in the top portion of the calibration certificate, and on the sticker that you'll get on the box of the sensor, will be what we call the reference sensitivity. The reference sensitivity is the 100 hertz data point of the sensor. So if you look in this list here of 10 points, at 100 hertz, that is the reference sensitivity that you'll see up here. The accelerometer industry, piezoelectric accelerometer industry, has standardized on 100 hertz as the frequency point of reference sensitivity. Okay. So today's discussion is predominantly talking about measuring vibration. However, you can use the exact same technology, piezoelectric crystals, to measure force and pressure. There's not a lot of applications for dynamic force and dynamic pressure out there, but we do offer that. Most of the pressure and force sensors in the marketplace today would be strain gauge based, but we do offer piezoelectric dynamic for very high frequency events, for pressure sensors where you would need 100 kilohertz type of data, or load cells where you're doing, say, drop testing, and you don't want displacement from the sensor. So today we're talking about mostly vibration, but the same technology can be used for other measurements. I want to talk today, let's start talking a little bit about that dynamic versus static measurement. So again, this presentation is predominantly centered around dynamic measurement, which is piezoelectric for our technology. But again, we also offer at Dytran static DC MEMS variable capacitive sensors. So let's talk a little bit about the difference in the two. Dynamic, this is a little bit self-explanatory, but the physical quantity of a dynamic measurement means either the pressure, the force, or the acceleration is rapidly changing over time. Some examples of those things would be modal analysis, NVH testing, turbine engine testing, transmission testing, brake testing, halt-has testing, things like that, where you have a high frequency rate. And then conversely, on the static side, the physical quantity being measured does not change as a function of time very rapidly. And so examples would be, the best example is the constant acceleration due to gravity. And the other example that we like to give is a bathroom scale. So a bathroom scale is a perfect transducer. What we're talking about today is a transducer. Transducer is a sensor that takes one form of energy and converts it into another form of energy. So your bathroom scale takes your weight, your mass, and converts it into a digital readout. For an accelerometer, we take acceleration or shock, and we give you an electrical readout. So that's what a transducer does. So dynamic versus static. If I took a piezoelectric dynamic sensor and a DC static MEMS sensor, and I had an application, let's say it's 50 Gs at 100 Hertz at 100 F temperature, I could use either of those two sensors in that application. And so there's a lot of crossover between the two technologies. And usually what dictates what sensor I end up using is literally the legacy of that measurement in the industry, or more importantly, the data acquisition system that's being used. In the automotive industry, the NVH world, the modal analysis world, typically almost always uses IEPE or dynamic sensors. And so even if the application could use a MEMS sensor, they're going to fall back and rely on their history and their experience with those sensors. And that goes the other way as well. When we visit flight testing in the aerospace world, they're set up with specific data acquisition systems, and that's usually what dictates the sensor that they use. Okay, let's move on. So now that we know what a transducer is, let's talk a little bit about what is piezoelectric technology. So the piezoelectricity, the technology that's inside the sensor, is a crystal. And so that crystal is either going to be a ceramic or some type of man-made crystal like quartz. And those crystals generate an electrical potential in response to an applied mechanical stress. And it comes from the Greek word piezo, which means to squeeze or press, or I like to say it means to change. So most of us are more familiar with strain gauge sensors. And a strain gauge sensor is a piezo-resistive sensor. So that means we're changing the resistance in the strain gauge. As you strain that gauge and you stretch the wire, you change the resistance, and that change is extremely linear to the amount of strain you're putting into the strain gauge. And that's the same thing we're doing with a piezoelectric sensor. We're squeezing that crystal, we're getting a charge output that's extremely linear to the amount of force we're putting into the crystal. It's like a sponge. The more that I squeeze, the more output I get. The less I squeeze, the less output I get. And again, it's extremely linear. These crystals that we use for measuring these piezoelectric crystals, again, are man-made in very, very high pressure autoclaves up to 70,000 PSI. And we use quite a few different types of materials at Dytran, mostly quartz and ceramic, but we do use others for high temperature applications. The one crystal that is known to man that is naturally grown is tourmaline, typically found in Russia and in Brazil, but you can find it in some other areas, but it's extremely rare and very expensive. It is very, very stable though over large temperatures. It's also used in jewelry and in witchcraft. So there you go, some information on tourmaline. All right. I like to show this slide because it shows the difference between shapes and sizes of different types of accelerometers. Here in the middle are these very, very ultra miniature single axis and triaxial accelerometers, extremely popular in automotive and aerospace testing. Over here we have our general purpose little miniature single axis. This is a very popular triaxial accelerometer. These are our MEMS sensors here. This is single axis, and over here is actually a 6th degree of freedom where we actually have gyros and 3 DC accelerometers output. This is a very, very high G range shock sensor, 100,000 Gs. And this is a seismic accelerometer, the opposite of this. It is 0.5 Gs, so measuring seismic activity or buildings and civil structures, things like that. So lots of different shapes and sizes. This is just a few of them, but it's always important to see what these things look like as we're talking about them. So now that we know what a piezoelectric transducer is, and we know what piezoelectric is, we know what the transducer is. So once we put the piezoelectric inside the transducer, we now have two types of sensors. So we have a piezoelectric charge mode sensor, which means that all we have is that crystal inside of the sensor. So literally inside of this sensor is just the crystal, and then we encapsulate it inside the housing, and we give you the output. It's what we call a self-generating sensor. A charge mode piezoelectric sensor is self-generating. You shake it, you get an output. But again, that output is in picocoulombs. So the engineering unit for charge is picocoulombs. And unfortunately, most data acquisition companies out there do not read picocoulombs. And so you need to convert that picocoulomb signal to a voltage at some point. We either do that inside the sensor or we do it outside in an inline charge converter or actually inside the data acquisition system itself. And so the charge mode sensor is just literally raw charge output. If I put the amplifier inside, and now I'm giving myself a voltage mode out of the accelerometer, I'm giving myself millivolts per G out, that amplifier that's inside that accelerometer has a name. We either call it IEPE or ICP. Others call it piezotron. Some people call it isotron. So there's lots of different names for it, but the IEEE organization has now standardized on the terminology IEPE, which stands for Internal Electronics Piezoelectric. And then a lot of people are familiar, though, with the term ICP as well. But they all mean the same thing. It's just the name of this amplifier that we all use to convert that picocoulomb signal to voltage mode. The only reason you would ever use a charge mode accelerometer is for temperature. Once your temperature exceeds the rating of the amplifier inside the sensor, then we have to convert over to a charge mode sensor and amplify externally. That temperature conversion happens around 300 to 350 F. Anywhere above that, then we have to go to charge mode. So a lot of our applications for, say, turbos or exhaust manifold or turbines are charge mode sensors because it's a high temp, hot, what we call the hot section, either of the vehicle or the turbine engine. Okay. We'll talk a little bit here about what's inside of an accelerometer. This doesn't usually come up. Every once in a while, someone does say, hey, I wish, could I get a shear mode accelerometer? 90% of all the sensors that Dytran designs, in fact, 90% of all the sensors in the industry are shear mode at this point. In the early days, the first 20 years of the accelerometer industry, they were all compression design. And we still use compression designs for industrial accelerometers and shock accelerometers. It's a very robust design. But today, as I said, 80 to 90% of our designs and sensors out there are shear mode. But they do have common traits and common components. So if you look here on the compression design, you'll see a base. For Dytran, almost all of our sensors are made out of titanium for mass versus strength. So we have titanium in the base, and then we have the stack here, happens to be on this sensor, 4 crystals. So we have 4 crystals summed together through insulators in between, and then this green portion is the seismic mass, usually made out of tungsten. This seismic mass then sits on the crystals, and then we squeeze this stack together with this preload screw. You could glue everything together. Some of our competitors do that, but we decide to screw it together. And we preload it to about 20% of the output, but because it's an AC coupled device, then it bleeds off immediately, and then from there we swing plus and minus around 0. Now, there's a couple flaws with this design, or I should say there's a couple design characteristics that are important to know. One is if I'm mounting this sensor to a thin structure, let's say a piece of thin sheet metal, and that sheet metal starts to warp and deform, that strain that I'm creating will induce right into the base from the test article, and because I'm coupled intimately straight to the crystal, if I have my sensor plugged into an O scope and I was looking at the output, but the sensor is just sitting on the table, but the table is warping, then I will get an output. And obviously I'm not seeing any vibration or shock. So this is what we call base strain sensitivity. And this sensor has a poor design for that. The other issue with this sensor is, let's take the sensor, plug it into an O-scope again, and then dunk it into a bucket of ice water. And when metal, of course, sees that immediate cold, is going to contract. So this screw is going to squeeze this crystal stack straight into compression. And if you look at an O-scope, it literally, the sensor will go to what we call full scale. It'll scream. The output will literally scream to full scale. And then once it sees that for a couple seconds, it'll settle out and go back to zero. But that immediate error that you're seeing is not based on vibration, just based on what we call thermal transient response. And so we've changed the design over the years to the shear mode design, which still has all of the same components. We still have the base. We still have the seismic mass made out of tungsten. We still have the piezoelectric crystal right here. And then we have this preload screw squeezing this entire stack together. But now, because we're on this post, we've decoupled ourselves from the base. So if this area here is seeing some kind of a strain, I'm not inducing that strain directly into the crystal. It's decoupled. And then secondly, if I dunk this in ice water, this screw is going to contract and put this entire system into a compressive mode. But because these crystals are polarized to only give us an output when we shear the face of that crystal, it does not give an output when we see a compressive force. And so this design is excellent for those two test characteristics. Okay, so this is what the crystal looks like once it's cut and polarized. And we use all kinds of different crystals inside these sensors, depending on the shape and size and design of the accelerometer. This is a cartoonish depiction of what's going on inside an accelerometer that's a shear mode design. This is the crystal is aligned next to another crystal. We are neutral charge when at rest. You can see the negative aligns with the positive, so we're neutral at rest. And then as I start to vibrate and shake, and I'm going acceleration in the up direction, I will start to align the crystals so that I get a positive output in the up direction and a negative output in the down direction. And so this deflection that you're seeing right here is obviously cartoonish, because the actual deflection on a piezoelectric accelerometer is in the angstroms, versus a strain gauge device where when you deflect a strain gauge, you get typically around 0.003 to 0.004 of an inch deflection. So there is a deflection here, but it's literally microscopic in the angstroms. Okay, let's talk about that voltage mode IEPE or ICP transducer accelerometer. It allows us to use either quartz or ceramic as our material. The charge mode sensors, we only use quartz for high temperature because it's much more stable over high temperatures, where ceramic is much better for low noise and low frequency applications. So it really depends on the application as to what crystal we're going to be using. Obviously, self-explanatory, and voltage mode sensor has an amplifier built in, so internal electronics. It's very stable over a broad temperature range. Again, we go typically minus 65 F to plus 320 F with our IEPE amplifier. Above that, we go charge mode. Okay. This is very important to understand that that IEPE amplifier, that ICP amplifier, does have a voltage associated with it on the input. It's 18 to 24 volts DC, But the key is that it's a constant current amplifier. So it needs anywhere from 2 to 20 milliamp constant current. Most data acquisition systems out there provide 4 milliamps as the power. But again, it's very important that we do not plug a standard 24 volt desktop benchtop power supply into the sensor, because it will damage the sensor. The output of piezoelectric accelerometers, voltage mode sensors, are 5 volts out. Okay, so it's AC coupled, 5 volts out. And so when you see an accelerometer with a sensitivity that says 10 millivolts per G, which is very common, that 10 millivolts, because I have 5 volts out, means if you do the math, it's a 500 G accelerometer, and 100 millivolts is a 50 G sensor. So we always get 5 volts out at full scale. And as we said, it's a very simple 2-wire schematic. I'm going to show you the schematic here in a second. So let's talk a little bit about frequency. Again, frequency is a very important part of selecting a transducer when we're going through the data sheet. Frequency is one of the most important things we look at. And as we look at different shapes and sizes of accelerometers, it's kind of hard to tell, but this sensor here is a seismic accelerometer the size of a coffee cup. So it's got internally, it has a lot of mass that's sitting on top of a big crystal, versus this sensor here has almost zero mass. It's almost just a pure crystal. And so as you can imagine, F equals MA, trying to move this sensor up and down has a very limited frequency response, probably a natural frequency of around 5 kilohertz with a usable frequency of around 500 hertz, where this sensor has a natural frequency of around 100 kilohertz with a usable frequency of around 20 kilohertz. So again, the high frequency, the upper limit frequency, is dictated by the design of the accelerometer. The mass, the material, the amplifier, all of the design goes into the limitation of the upper frequency. The lower frequency is dictated by the design of the sensor internally at the factory, and that's called the discharge time constant. So it's a formula that describes the roll-off from once we engage the accelerometer, we shake it, we get an output, and then once it goes back to zero, that time frame is called the discharge time constant, and there's a formula for that. I didn't put it in here, but if you're interested, I could get that for you. It is factory set, can't be changed once you get it. And again, you look at the data sheet, and we don't typically tell you what the actual formula is or the actual ratio of the discharge time constant is on an accelerometer. But what you will see is the low end frequency. So if you look at different data sheets of different accelerometers on the low end frequency, you will see different specifications. You might see a half a hertz or 1 hertz or 2 hertz or 5 hertz. And the difference in that low end frequency is a difference in the discharge time constant. And it's just important that if you're going to be measuring with multiple sensors and you care about low end frequency, that you use a sensor, all the sensors have the same discharge time constant. Otherwise, you will get different data. It doesn't mean the data is wrong, but you will get different data at low frequency if you have sensors with different discharge time constants. So that's one of the important aspects of understanding the low end frequency part of your sensor. This is the graph of a typical frequency response of a piezoelectric accelerometer. It's also the graph of any transducer, to be honest. Our transducers are designed typically between 0.2 and 0.3% of natural frequency is the output. We want to stay as far away, of course, from the natural frequency as possible. And then we also, of course, want to stay away from the low end roll off. This is where we start to roll off on the low frequency. On the data sheet, you'll see where this starts to roll off at, we give you the 5 hertz point, the 10 hertz, 3 dB, and 6 dB. And you'll see the sensor here is 5% at around 8 hertz, etc. And then the roll off down from there. This is that very simple schematic, the IEPE ICP schematic that we talked about before. You can see how simple it is, but very, very innovative. And 50 years later, we're all still using it today. Okay, let's talk a little bit about the charge mode accelerometer. Now we're moving away from the internally amplified voltage mode sensor, and we're taking the amplifier out, and now we have a charge mode sensor. When you have a charge mode sensor with a picocoulomb output, at some point you have to amplify that. So you'll have an amplifier either inside your data acquisition system or an inline charge amplifier, or what we call a charge converter. In between the sensor and the amplifier now is the cable. And it's very important that you have a proper cable, because if you have the wrong cable put in place, you will get what we call a triboelectric effect. If the cable is not properly designed for these charge mode sensors, then what happens is the cable itself, as it's moving back and forth, being vibrated, will build up spurious charge. And on an O-scope, it doesn't know if the sensor is vibrating or if this is triboelectric noise. And so I'm going to show you a little video of this sensor here. This is a piezoelectric high temperature turbine engine sensor with a cable attached to it, and it's the wrong cable. This is just a standard Teflon cable, and unfortunately it's not designed for these charge mode sensors. So as we whip and move the cable, it's building up spurious charge inside that cable, and there's nothing to dissipate it. And so it goes right into the data acquisition system, and it looks like a vibration. So let's get started here. And you'll see as we start to whip the cable back and forth, you can see how much output we're generating, and yet the sensor is sitting still, not moving at all. And so this is what we call the triboelectric effect. Now he's going to stop here in a second, and he's going to change the cable out to a red cable that is specially designed to dissipate that spurious charge as it's being built up, and does not allow that charge to go into the data acquisition system. So here he goes, changing the cable to the red cable, and now you can see the output as he starts to whip the cable, that we have a very clean signal compared to prior. Now it's very important, the other aspect of this is it's important to tie your cable down all the way back to your data acquisition system. We don't want to see the cable whipping around like this, because that is this little bit of noise you do see on here is the whipping of the cable. Okay, so it's important to tie your cables down and use a proper cable. All right, let's talk a little bit about do's and don'ts. Some of these are very self-explanatory as far as piezoelectric accelerometers. Do not drop your sensor on a concrete floor. If you look at a data sheet of a piezoelectric accelerometer, you'll see that it says the measurement range is, so let's say 500 Gs, for example, but there's an overload of 5,000 Gs. It says maximum overload 5,000 Gs. Well, that's in case you drop it. That's exactly what that's for. So it's okay to drop it, say, from 3 feet, but if you drop it from 6 feet or 5 feet, you definitely could damage and break the sensor. As we already talked about, make sure you don't use a benchtop power supply. Make sure you use proper power. Make sure you remove the sensor with a proper instrument, not a hammer and a chisel. Make sure you do calibrate your accelerometer at least on a yearly basis. And we'll just leave it at that. And then the opposite, of course, for the do's. And we'll skip over that. Won't spend a lot of time on this, but we do offer for IEPE accelerometers, we offer TEDS capability. TED stands for Transducer Electronic Data Sheet. And basically, it's like storing the calibration certificate inside the accelerometer proper. And when you plug it into a data acquisition system that is plug and play compatible with TEDS, then it automatically calibrates. It's basically like putting your mouse on your laptop and it automatically just starts to work. It's the same concept, plug and play. So we do offer this. It's an IEEE standard called IEEE 1451.4. And this is the information that is stored inside of that E-chip, EEPROM chip inside the sensor. All right, let's talk a little bit now about mounting accelerometers. There's only 3 ways to ever mount an accelerometer. You can glue mount it, you can stud mount it, or you can use a magnet. We are starting to see more and more customers using magnets to mount their accelerometers. but most customers will either stud mount or epoxy glue mount the sensor. Some customers are not able to drill and tap into their product, like a cell phone, let's say, and so they do have to glue the accelerometer. And so there are benefits and features to both of those methods. Let's look at the bottom here, stud mounting first. By stud mounting the sensor, you can get as close to the natural frequency as possible of the accelerometer. In this case, you can see it's almost out to 28 kilohertz if properly mounted. But what we do want to highlight is when we adhesively mount, when we glue mount an accelerometer, we are adding a spring mass system to the measurement. And so depending on how good you are at mounting an accelerometer using glue, that perturbation that you see there could be down here or up closer to the natural frequency. If I did it, it would be way down here because I don't do it very often. So this is definitely an art. It's definitely takes some experience to properly glue an accelerometer to your test article. And then on the magnet side, you can see you're limited to around 3 kilohertz with a rare earth magnet. That's redundant. If you are stud mounting an accelerometer, most of the accelerometers that we offer at Dytran have a female thread so that your stud is provided separately. And that way, if anything did happen and you accidentally sheared the sensor off or something catastrophic happened, you're not going to damage the sensor. You're going to damage a very inexpensive stud. And you can see if this sensor here, which has an integral stud on it, gets broken, then the whole sensor needs to be repaired or replaced. And here in a second, we'll talk about surface finishes as well. So on a surface finish, you want to make sure that you follow these steps to get a proper mounting, especially if you care about high frequency. You want to clean the mounting area thoroughly with compressed air to remove all traces of surface contamination. Some people even sand it down and clean it off. And then, very importantly, add a light coating of silicone grease in between the sensor and the test article. That way you fill in all the gaps and crevices to ensure a close contact, an intimate contact of the surface imperfections between the sensor and the mounting area. So this area here, we want to make sure we get as much of the surface finish on the mounting surface as possible of the sensor, and that silicone grease helps in that regard. And I'll skip that. Another very important aspect of mounting your accelerometer is the use of bases. We have many, many types of bases that we offer at Dytran. You can get anodized aluminum bases that provide electrical isolation for your test and your sensor. You can get glue-mounted bases, stud-mounted bases. We have high-temperature bases, etc. So just like the stud that we talked about, the base, if you're going to put on, take off, put on, take off, put it on, take it off, put it on, take it off, the base becomes your sacrificial part instead of the expensive, more expensive sensor that you're dealing with. So very, very common to use bases in between the test article and the sensor. And I'll skip the magnet, but that's a magnet. Now I want to talk about isolation. If we go back and we look at this list of sensors real quick, this picture of sensors, most of the accelerometers that you're looking at here are not electrically isolated. And so making sure that your sensor is electrically isolated is super critical, depending on the test, of course, but either making sure the sensor is isolated or provide isolation to the test, either through a base or the adhesive or through some other material in between the sensor and the test article. So what I'm going to show is a quick video. We have this metallic structure that we've energized, and then we have the first sensor we're plugged into is a non-isolated sensor. We're going to show you what happens. Then we go to an isolated anodized aluminum base, and then we're going to go straight to an isolated accelerometer. So you can tell the difference here. You can see that sensor right around the connector here is a base. That's the electrical isolated base on that sensor. So let's get the video started, and you're going to see we're going to impact with a hammer. And this is the impact of the hammer here. And then we're swamping the data. This is the actual accelerometer receiving the data from that hammer, but we can't hardly even see it because we're swamping the data with this 60 hertz cycle noise. So if we did an FFT, you would see very plainly 60 hertz noise showing up. So now we're going to switch here in a second. We're going to move the sensor, the cable, and sensor over to the isolated pad. So now you can see as he's impacting a very clean signal from the accelerometer and great data. And then he's going to move it straight to the isolated sensor, and same thing, great data with no noise. So again, very important isolation, electrical isolation of your sensor. The next videos, I'm not going to actually show the video because he actually doesn't do anything in the video but show himself mounting the sensor. Kind of boring. But what I do want to show is the data here in the graph. So what he's showing here is we're stud mounting an accelerometer to a shaker, and this is our reference accelerometer. So we're mounting this sensor to the top here, and then down here we're going to glue this base to the shaker, and then mount the accelerometer to this glue base. And he actually gets pretty good data here. It's kind of hard to tell, but on the stud mounted data sensor above here, he's getting pretty flat out to around, I would say, about 12 kilohertz. And then down below here, when he's gluing the accelerometer, he starts to creep at around 8 kilohertz. By about 10 kilohertz, he's way out at 11. He's got the perturbation. This is the spring mass system he's introduced into that measurement. But he still did pretty good mounting that sensor using super glue. And then on the next page, we're going to show using wax. On the top screen, on the top graph here, we show a really good job using wax to mount the accelerometer. And we get pretty good data out past a kilohertz here. I'm sorry, out past almost a 10 kilohertz using wax. And but when he wanted to show putting too much, an excessive amount of wax, what happens to your data. And you could see at around 2-3 kilohertz, it starts to take off. So again, the point is, if you care about low frequency data, it doesn't matter how you mount the sensor. You could probably use bubble gum, but if you do care about 10 kilohertz, 5 kilohertz, 7 kilohertz, then mounting your sensor properly is very important. Let's talk a little bit about the transducer selection. We talked some of this already. Again, we start with size and mass. We care about mass loading our product, so that's what we start with first. Then we get into these other very important questions: the vibration level, the frequencies of interest, maximum, minimum, temperature, the environment. Is it inside, outside, mud, snow, rain? And then we talk about cable length, the connectors, data acquisition system, those types of things, how we're going to mount it, etc. So great questions here for selecting a transducer. We have on our website, we have an excellent product configurator that allows you to configure specifications, and a sensor is recommended to you, or you can just call Tony and get his suggestions. We already talked about this during the presentation. I'm going to skip that, and that's redundant. And we're right at 1 hour, so I'll wrap up with that. Again, if there's any questions, please feel free and jump in. Otherwise, thank you for your time today. We really appreciate it. You have my email address if you do want to email me any questions as well. So thank you very much for joining us today on this presentation.
If anyone has any questions or would like to know anything else about any of the types of accelerometers that might not have been mentioned here, I think 6 degrees of freedom,
Yeah.
digital Excels, things like that, just let us know. We're more than happy to do this again and be a bit more specific as to, something you might be interested in. So.
Yep. Thanks, Tony.
Hello, this is Mark. I have just a question. If I can go back to the cable selection topic of when you're whipping the cable.
Yeah.
What was the key difference that you mentioned? I think you probably mentioned it. I just missed it. The key difference in the red versus the white cable.
Yeah, great question, Mark. So the difference is internally, the white cable doesn't have it, but the red cable is the way it's built. It actually dissipates the spurious charge that's being built up. I forget exactly the mechanical phenomenon that's difference between the two that allows that to happen. It's the way they wrap the cable is what it does, is what it is. And what I would recommend is if our customer has both types of sensors, charge mode and IEPE or amplified, I would recommend you just always use the low noise red cable in everything you do because it's the safest thing to do.
Okay.
Yeah.
Now, I have experience with the low noise cables and flight test, and oftentimes we would have to purchase a pigtail setup at some point, or we go to another connector, and then at some point we have to add a pigtail connection, which is always a source for noise and a trouble. Is there other kits, anything available to better fabricate, maybe even just add your own connector versus splice that would help resolve some of the noise that you're going to see at those connections?
We do offer some splicing kits. It's not easy, so if there's any way we could do it for you, that would probably be the ideal way. But just to make sure that the shielding is carried all the way through would be the most important aspect of it. And then the least amount of junctions, as you can imagine, to your point, to your experience, as possible. Yeah, limits that noise injection. But yeah, whenever you do have an opportunity for that, again, we'd be happy to look at potentially doing the connectors for you, terminating to the right connector for you instead of the pigtail, so that we can properly put that shield all the way through. Is one thing that we could do.
Yeah, these were unfortunately something we were doing all too often. It was not a leave-in-place setup.
Yeah. I know the flight test. You guys in the flight test world have tons of challenges trying to route this stuff through these aircraft.
Okay. Well, thank you for
where were you at before?
I was at the last 4 years up till recently. I was working for the Mitsubishi Regional Jet Project. Now they call it the Space Jet. Working on the M90. I was the lead engineer.
Up in Seattle? Up
in Moses Lake, Washington, was where the flight testing is occurring. Correct.
Oh, okay. How did Tony find you? Are you located in Indiana or are you in Washington?
I'm in Dayton, Ohio now. I moved back for family reasons.
Okay.
And just as I was about to start getting employment, everything fell apart.
Yeah. What a crazy time for this.
Hey, Kevin.
Yeah.
This is Tony Sum. There's another question that someone entered in the meeting chat. Sam Olson asked, if you have issues with bolts backing out, loosening your sensors from object being measured, would applying something like Loctite on the bolt affect the data acquired?
This is the bolt to mount the sensor down, or is that what I heard?
Maybe, yeah, it's
not the connector, it's not the cable.
He says yes, it's the bolt to mount it down, yes.
No, because you're still intimately tied to the stud. So that's a very common practice to keep it from backing out.
Cool.
Yeah. Mark, by the way, if you ever want to meet me at Warped Wing, I would love to do that. So.
I'm sorry, what is Warped Wing?
Is that a microbrewery in the Oregon district of Dayton, Ohio?
Oh, okay.
Named after the propeller designed by the Wright brothers.
Okay.
Anyway.
I'm a Dayton native. I worked for the University of Dayton Research Institute for about 10 years. So.
Excellent.
Just
Yeah, we're
Good
working
to be
with
back in the area.
Quicksilver. Do you know Quicksilver?
I've heard of them.
Yeah, they're in Seattle. They do flight testing. They did it for Mitsubishi up there at Moses Lake.
Okay.
So that's, I could get you in contact with them if they're hiring.